Okay, welcome everyone. Thanks for joining us for Module 7 in our 9-part CUDA training series. My name is Tom Papa Theodore. I'm with the OLCF. Also on the call, we have Helen He and Kevin Gott from NERSC. They're the organizers on that end. Today we're joined by Bob Cravella, Max Katz, Robbie Searles from NVIDIA, and Bob will be giving a talk today on CUDA concurrency, as the name of the training event suggests. So that'll be a presentation for about the first hour, and then Max Katz will follow up afterward by walking through an example program that will sort of bring together some of the ideas that Bob had covered in the talk. So today, Summit is down for maintenance along with our other internal systems that have that same architecture. So Max is going to walk through this example program on Cori GPU at NERSC instead of on Summit like we typically do. So unfortunately, this does mean that the folks who might have wanted to work through the example problem and only have access to Summit won't be able to do that today. But Max will walk through the example, and I'll get the recording up quickly afterwards so that if you want to walk through it on your own, following along with the recording of Max doing it afterward, you'll be able to do that. Okay, if you have questions during this talk, feel free to drop those questions into the Zoom chat, and Bob will tackle those when he sees the opportunity. And then afterward, you can ask questions during the hands-on, or maybe we should just call it demonstration session. You can ask those just by unmuting yourself if you want to. But stay muted for the presentation itself as we're recording this, and we want to get a clean recording. Okay, as always, you can go to the event page and get the presentation, so a PDF of the presentation, and find the homework link there already. All right, and with that, I will hand things off to Bob if you are ready to go.
Thanks, Tom. I think you've covered all the logistics. On behalf of NVIDIA, I'd like to thank the folks at Oak Ridge and NERSC, including Tom and Helen and others who have invited us to do this and provided all the logistics. And I think Tom has covered the logistics really well, so I'm just going to thank my colleagues Max and Robbie for joining me, and we will get started. So if you've been following along this series, then I would like to say kudos to you, because we are now on session 7 of 9, and we've covered all of the basic logistics of how to program in CUDA already, actually some time ago. And as you know, after around the 4th or 5th session, we transitioned into some topical areas for investigation. This is another topical area that we'd like to investigate. And concurrency is actually a really important part of CUDA, because what you will discover as you do more and more CUDA programming is that there are substantial optimization opportunities by leveraging concurrency. Really, concurrency doesn't do much of anything in terms of unlocking new calculation abilities or new algorithm solution techniques. What concurrency really is largely about is taking advantage of the opportunities that exist when you have multiple processors in a system to leverage all of those processors to their maximum ability. And we're going to study a number of different concurrency scenarios that are enabled within CUDA that allow you to do exactly that. So we'll start with a slide on motivation. We're going to start, I think, in a place that's very recognizable to all of you. We're going to need to do a brief aside on something called tin memory. And then for the bulk of the presentation, we'll be covering the mechanics and the different use cases or scenarios where concurrency may be used. And of course, at the end of this session, we'll have some suggestions for further study, and there is a homework as well, just like we've done with all of the other sessions. So first of all, what I'd like to do is take us back to session 1. And in session 1, we learned that the basic CUDA programming model is what I refer to as a 3-step sequence. You copy data to the GPU, you run or execute your CUDA program. We learned that's called a kernel. You run or execute your kernel, and then you copy the results back to the host. And of course, there's variations on this theme, but nevertheless, every single CUDA compute program that exists on the planet follows this 3-step sequence in one form or another. And we learned that even things like managed memory don't really substantially alter the fact that each one of these 3 operations is necessary in some fashion for a properly functioning, useful CUDA program. If we write our CUDA code the way we've learned to do it up until now, where we write a CUDA memcopy from the host to the device, and then we launch a kernel, and then we write a CUDA memcopy operation from device to host. What we're going to observe in a profiler, if we run that code and then observe what's going on when, and we could think of that as a timeline view, as we proceed through the execution time in our program, what is happening at each point in time. If we imagine that we have a profiler that's giving us a timeline of our execution behavior, we would see something that looks like what you see on the top half of this slide. We would execute our first CUDA memcopy operation, and then for a period of time, that would occupy our timeline. And during that period of our timeline, the CUDA memcopy operation is running, data is moving from host to device. When all of the data has moved from the host to the device, the CUDA memcopy operation completes, and then our kernel launches. And we see our kernel launch in blue on the timeline, and then we have our CUDA memcopy after the end of the kernel. And so one of the observations we can make is that things tend to serialize. The kernel execution doesn't begin until the previous operation is complete, and so on. This results, of course, in a duration, the total execution time of our program, which is basically the sum of the first CUDA memcopy operation, the kernel duration, and the second CUDA memcopy operation. And they're all serialized, so that's just adding them together. The motivation that I want to plant and that we're going to explore during this session is to say, wouldn't it be nice if there was a way to overlap these operations? And what would be required to do that? And what kind of mechanics in CUDA are we going to need to arrange that if such a thing is sensible and possible? Now, the motivation hopefully should be clear because it's printed out on this slide. Ultimately, what we're after here, 99 times out of 100, is we are after an improvement in the duration, a shortening of the duration, therefore an improvement in the overall execution time of our code. Remember, the only reason that people use CUDA is to make their code run faster. And so if I can teach you a way to make your code run 2x faster or 3x faster, that can be very significant. That could be a very, very, very important optimization for you to consider in your CUDA programming experience and exercises. In fact, many folks would say this is at the top level of CUDA optimization tactics that you should be familiar with and ready to deploy. So if we go back several sessions, we learned about 2 top-level CUDA optimization objectives that primarily applied at the coding level within the kernel. This optimization objective, concurrency, especially the way I've depicted it here on this slide, is something that you should always be familiar with because it's low-hanging fruit, and it's a fairly mechanical process to achieve this kind of concurrency. So let's drill into this. In order to drill into this, we're going to have to do a brief aside on something called pin memory. We're going to be building up the bits and pieces, the blocks, the capabilities that we need in order to create concurrency, in order to have concurrency occur the way we want it to occur within CUDA, executing on a GPU. And so the first topic that we're going to need to unpack is something called pinned memory. A modern operating system like Linux or Windows has underneath of it a memory subsystem that has a certain level of complexity to it that may not be evident to the programmer. Basically, the idea is that a modern operating system like Linux or Windows will separate the idea of a virtual memory space from physical memory, the RAM, the system RAM that's used to store data that's being used by the program or by the system. And this separation of space is going to introduce typically something called paging, which is nothing more than a subdivision of their respective spaces, the virtual address space and the physical RAM, into usually fixed size blocks of a certain size, like 4K bytes. So we'll divide up all of our physical RAM into 4K byte chunks, and we'll logically divide all of our virtual address space into 4K byte chunks. And when, as a programmer, I do an allocation, like using malloc or new, for example, that's going to carve out some virtual address space, an area in my virtual address space map that represents the area, the location, where this allocation is going to be stored. When I actually intend to use that allocation, when I write code that touches that allocated pointer, for example, the memory subsystem built into the operating system will observe that event and will say, okay, I actually need physical RAM now to support this. And it will bring that physical RAM, it will allocate physical RAM, it will carve out space in the physical RAM, again, by chunks called pages, and it will provide those pages, and it will provide a mapping from the virtual to the physical, a mapping from the virtual address space to the RAM, if you will. There's a lot of complexity here, and I'm glossing over many, many details. It's not my objective to give you a complete tutorial on a demand page virtual memory operating system, but we're going to cover, hopefully, just enough of the fundamentals so that you understand what pinned memory is and why it matters. So one of the benefits of this sort of virtual and physical mapping and the ability to separate the virtual space from the physical resource that's backing that virtual space is there's actually a number of benefits, but one of the benefits, perhaps one of the most obvious ones, is that from a programming perspective, I can now work with data sizes, allocations, if you will, that are larger than my physical RAM. That's actually a significant benefit. And so one of the prime benefits of a demand page virtual memory system is exactly that. There's other benefits as well. But nevertheless, that's one of the things that people are primarily interested in, so that if I have a machine with 8 gigabytes of RAM, I can actually write a program that operates on 16 gigabytes of data. And it will appear to just work, almost more or less as if I had 16 gigabytes of physical RAM. And that's one of the primary benefits. So that's the basic idea behind a demand page virtual memory operating system. And both Linux and Windows have this characteristic. One of the downsides of this is that when I go to touch data, it may or may not be physically resident in RAM. And if it's not physically resident in RAM, the operating system has to get involved and do a bunch of footwork, and eventually it will bring the data into RAM, and my program can proceed at that point. But if the data is not physically resident in RAM, that can be a performance issue, and it also means we need interaction from the host operating system. Now, when we're talking about concurrency in a GPU or concurrency in CUDA, some of the primary operations that we want to overlap, in other words, that we want to allow to occur at the same time, are memcopy operations and kernel operations. And we know that both memcopy operations and kernel operations are kicked off, they're launched, if you will, by host code. So we need to be able to have a significant amount of flexibility to allow these operations to occur at the same time. And the way that we're going to do that underneath the hood is we're going to introduce a new API. We'll see that on the next slide. But we're going to, through this new API, we're going to allow something called copy engines to operate asynchronously, independently, that move data from one place to another. And those copy operations, fundamentally, in order for them to be able to have this flexible behavior that they can operate asynchronously and kick off at any point in time, they're going to require that the data be physically resident in RAM, in physical host memory. So we can't have this demand paging system let some of this data be paged out, so to speak. In order to signal to the host operating system that we don't want that behavior, this demand paging behavior, we'd like the data to be always physically resident in RAM, and we'd like the mapping from virtual to physical to be fixed and unchanging for the life of our program. We have to use a special allocator, and that special allocator for CUDA is provided by the CUDA API. And the allocator that we're going to introduce is called CUDA host alloc, and there's a corresponding free operation called CUDA free host. Okay, so this is a new part of the CUDA runtime API. And CUDA host alloc is going to operate roughly in a similar fashion to malloc, except the returned pointer, the pointer that gets the allocation, is going to be a pointer to pinned memory. Pinned means that the allocated pages are physically resident in RAM, in CPU host memory, and they will not move. Okay, so one of the drawbacks of this pinning operation, and why we don't use it all the time, is that it interferes, if you will, or it reduces the effectiveness of the demand page virtual memory system to achieve the objectives that it has. So we're working in a trade-off situation here. Okay, so at the bottom of the slide, you see that pinned memory is essentially removed from the host virtual pageable memory. Okay, pinned memory, in a sense, you could say is the opposite of pageable memory. It's non-pageable memory. In addition to the CUDA host alloc and CUDA free host API, and you may, in CUDA code, there's another API called CUDA malloc host. It's very similar to CUDA host alloc. But in addition to the CUDA host alloc and CUDA free host API, which take a pointer, provide a new allocation, and make sure that it's pinned, there's also an API called CUDA host register and CUDA host unregister. The idea here is that you've already created an allocation, let's call it a pageable allocation, using an allocator like malloc or new, and now, later on, you decide you'd like this to no longer be pageable. You'd like it to be pinned. Well, CUDA host register can do that. It will take an existing allocation and simply pin it for you. And at that point, after the CUDA host register operation, that memory is no longer pageable. And if you want to release that behavior but still keep the allocation, then you can use CUDA host unregister to do that. So there's a question in the chat on this slide. Does using pinned memory bigger than physical memory size cause more swapping operations within the OS? That is actually an illegal behavior. So the OS will only allow you to pin an amount of memory with an upper bound of the amount of physical memory that you have. And hopefully the reason for this is the obvious. When you say to the host operating system, I would like to pin memory, you're saying, give me a piece of RAM to store this in. The most amount that you can do of that is limited by your physical memory. So if I had 8 gigabytes of memory, it's impossible for me to physically pin more than 8 gigabytes of memory. And in fact, the host operating system needs some of that 8 gigabytes. It can't give it all to you as the application programmer. So what will happen is if you do CUDA host alloc on a large enough allocation, or for a group of allocations in aggregate that are large enough, you'll eventually get an out-of-memory error. So one of the errors that can be returned by CUDA host alloc, just like with an allocator, you can run out of memory. With CUDA host alloc, you can run out of memory as well. The type of memory or the type of resource you're running out of is a pinned resource, and that's going to be physically limited by the amount of physical RAM. So it's impossible, generally speaking, to pin more memory than the physical memory size. And the implication, to expand on the question and expand on the statement at the bottom of the slide, is if I pin a large percentage of my memory, let's say I have 8 gigabytes and ask for 6 gigabytes of it to be pinned, or 7 gigabytes of it to be pinned, you're leaving very little space for the host operating system to do the things that it wants to do. That can severely impact the performance of your host code for a variety of reasons, for more than one reason. So this is a trade-off. Pinned memory has some advantages, but we don't want to just pin everything for no reason. In fact, we want to be careful about our usage of pinned memory, and we generally like to restrict the usage of pinned memory so that we're not impacting the performance of the host operating system. Beyond that, I'm not going to be able to give you any sort of metrics or formulas. You're going to have to experiment yourself to figure out what's manageable and at what level you start to impact host performance. Yes, pinned memory is just like a buffer that's always present in physical RAM. That's exactly what it is. Okay, so let's continue. That was our aside on pinned memory. Now we're going to transition into another building block that we need called CUDA streams. Streams are a mechanism, an API, a set of APIs, if you will, within CUDA that allows us to organize concurrency. okay? It allows us to specify to the CUDA runtime what things we want to happen in what order. In order to get to this level, we're going to introduce one more building block that doesn't necessarily directly have to do with concurrency, and that additional building block is called CUDA memcopy async. So we have learned already, using the programming techniques that we've studied over the last several sessions, that kernel launches are asynchronous with the CPU. That means the CPU thread, when it launches a kernel, doesn't wait for the kernel to finish. It launches the kernel and then it continues on with CPU code, whatever's next for that thread to process. However, we learned that CUDA memcopy operations, such as what we've been using already, are blocking. They block the CPU thread. When the CPU thread runs into a CUDA memcopy operation, the semantics are that all previously issued CUDA activity must complete before that CUDA memcopy operation will begin, and before the CPU thread is released from that CUDA memcopy operation, the CUDA memcopy operation must complete. So it's actually synchronizing and blocking, if we wanted to get into the details. It's synchronizing because it forces CUDA activity on the host, on the GPU to complete, and it's blocking because it blocks the CPU thread. Okay. In addition, what we're going to learn now is that all this time, without knowing it, we've been operating in something called a default stream. When you don't use an explicit stream, when you don't use any aspects of the stream API, all of your work is being done in something called the default stream. So there is stream semantics being applied. And one of those stream semantics that we're about to learn is that CUDA calls issued into the same stream are always serialized. We'll get into more details on that in just a moment. Okay. So in order to break this blocking behavior, we know that a kernel launch is asynchronous, but we know that CUDA memcopy is blocking. And we're going to need to break that blocking behavior in order for us to be able to schedule concurrency the way we want it. So we're going to introduce a new API called CUDA memcopy async. And in a nutshell, what this does is the same thing as CUDA memcopy, except that it takes a stream parameter. We're going to talk about what that is. And in so doing, it allows this operation to become asynchronous, which means the CPU is released from waiting for that to complete. It may or may not be complete by the time the CPU thread moves on. And this operation now has the opportunity, unlike CUDA memcopy, it has the opportunity to execute concurrently with other operations, both kernels and memcopies. Now, when we're talking about two memcopy operations, in other words, two operations that are CUDA memcopy async, to get those to execute at the same time in the timeline, the only way that's normally possible on GPUs is if one of those operations is in one direction and one is in the other. In other words, one is host to device and the other is device to host. In fact, that's primarily the concurrency we're after. Concurrency in the same direction is a much more obscure topic, and it's not something we're very interested in right now. So the primary concurrency need that we have is to schedule operations that copy data from the host to the device and from device to host at the same time. And CUDA memcopy async, when properly issued with a proper stream, can do exactly that on most GPUs. So what is a stream? A stream is a sequence of operations that execute in issue order on a GPU. And as we're about to see, we can have multiple streams. We're going to learn how to create streams in just a moment. Therefore, in a given stream, operations execute in the same order. In order to overlap, which is sort of the opposite of in-order execution, in order to have two things execute at the same time, they can't be serialized. They can't be forced to execute in order. That's what we mean by overlap. In order to overlap, therefore, we cannot overlap two operations issued into the same stream. In order to overlap two operations, they have to be issued into different streams. Okay. So what I'd like to do, I'm beating a little bit of a dead horse here, but stream semantics tends to be one of those things that people struggle with at first. And what I'd like to do is to focus your attention on two, I think, fairly straightforward concepts. And if you use these as a rigorous tool, you will be able to understand streams. You'll be able to sort them out. If you focus on these two things as the key to understanding, you will be able to both understand how streams work and understand how to schedule things so that you can achieve a desired concurrency scenario. Remember on that first slide, we presented an ideal concurrency scenario where a memcopy, a kernel, and another memcopy were all executing at the same time. So we're learning how to do that. The stream semantics are just two. And the first one is two operations issued into the same stream will execute in issue order. I'm not talking about operations that are next to each other or not next to each other. That doesn't matter. It's a very simple concept. If A is issued sometime before B, in other words, it appears before the issue of B in your code, then operation A and B issued into the same streams will execute in issue order. A is guaranteed to be finished before B begins. It doesn't matter if these two things are right next to each other or some distance apart. That's the first concept of stream semantics. Two operations into the same stream will execute in issue order. The only other concept that we need to understand and internalize to understand streams is that two operations issued into separate streams have no ordering relationship prescribed by CUDA. No ordering relationship means CUDA doesn't tell you what's going to happen. But if we want to have two things execute at the same time, overlap, our stream semantic 1 isn't going to get us there. So the only way that we're going to get there is by taking advantage of stream semantic number 2. Okay? And therefore, if we want overlap, this is not a sufficient condition, it's a necessary condition. If we want overlap, those two operations must be issued in different streams. If I want to overlap a kernel with a memcopy, I better use CUDA memcopy async because that takes a stream parameter, and I better make sure the two streams, the one associated with the CUDA memcopy async and the one associated with the kernel, are different. If they're the same stream, no possibility of overlap. The operations that we have in view right now are mainly a CUDA memcopy async or a kernel call. That's primarily the CUDA concurrency scenario that we started out with as motivation on our first slide. However, there are other CUDA API calls and other CUDA operations that take a stream parameter. And so those stream parameter enabled calls all obey these stream semantics. One of those that we'll talk about on a coming slide is something called stream callbacks. So let's start to unpack the syntax, and then we will look at some examples to build our understanding of this. First of all, we have some requirements, and the first requirement that's often forgotten is that if I want to have a CUDA memcopy async operation that is overlappable, that can be scheduled concurrently, running at the same time as another operation, if that CUDA memcopy operation, CUDA memcopy async operation, has as one or more of its targets a host pointer, which is usually the case, host to device or device to host, one of the two pointers will always be a host pointer, then that host pointer must point to pinned memory. Okay, that's why we introduced pinned memory, and hopefully the reasons for that are somewhat clear. We have an engine, a mechanism called the CUDA copy engine, and that CUDA copy engine requires the pinned nature in order to be able to kick off at any point in time. The other requirement we have is that these two operations, let's say it's a kernel and a memcopy, must be issued in different non-zero streams. We'll see what the zero or the null stream is in just a moment. So now let's take a look at some of the syntax here. First of all, streams are something that you can create. They're a CUDA type, and we identify the type as a CUDA stream T. And we first say that we have streams. We declare our streams, stream 1 and stream 2 in this case, kind of like saying int A, comma B. Okay, that's what we're doing here. We're saying CUDA stream T, that's a type, and we have a named stream called stream 1 and stream 2. You could name those anything you want, just like any other variable. Okay, I could name them X and Y if I wanted to. That's not enough, though, in order to have those streams be usable. After we declare the streams, we have to create the streams, which is basically alerting the CUDA runtime, which is something like an operating system that manages the GPU. We have to alert the CUDA runtime that we will use these named streams as streams. And so we do that by using a CUDA API call called CUDA stream create. We pass a pointer to the variable. That's why we're taking the address of stream 1 and address of stream 2. We pass a pointer to the variable, and after the completion of that call, that stream 1 and stream 2 variable or handle can be used to reference a stream that the CUDA runtime knows about. Okay, so the CUDA stream create creates an association with your handle and a stream that the CUDA runtime can manage. Once I have those streams created, I can use them in API calls that accept a stream. So one of the things that we haven't spent much time on yet, we'll talk about that in a minute. So first of all, in this example, we want to issue a CUDA memcopy async operation. And we learned that the CUDA memcopy async operation syntactically is like CUDA memcopy, except it adds a stream parameter. And that's exactly what we see here. We have two pointers, destination and source, a size parameter, that's the size of the transfer in bytes, a direction, that would be typically CUDA memcopy host to device or CUDA memcopy device to host. And now we're adding a fifth parameter called stream. And in this case, we're using one of our named streams that we've already created called stream 1. We now imagine that there's this timeline called stream 1, and we've placed our CUDA memcopy async operation in that. And after everything else issued into stream 1 is completed, that CUDA memcopy async operation will run right then. Okay? But it's an async operation, which means the CPU thread can continue whether it's complete or not. And therefore, the CPU thread proceeds on to the kernel call. And now we're going to learn something new about the kernel call, and that is our triple chevron syntax has additional parameters. This is something we haven't spent much time looking at, but there are actually 4 possible parameters or arguments that you can pass in the triple chevron syntax for a kernel launch. The first 2 we're pretty familiar with. The first is a specifier for the dimensions of our grid. It could be a dim3 type, or it could be a scalar quantity. The second parameter is the dimensions of our block. It could be a dim3 type, or it could be a scalar quantity. The third one is actually the size of the dynamically allocated shared memory that will be provided to the kernel. We haven't spent much time talking about the difference between statically allocated and dynamically allocated shared memory, but that's what this parameter is all about. Most of our examples so far have used statically allocated shared memory, and for that we wouldn't need to pass any, so we can use 0 here. And then the fourth parameter is the stream parameter. If we omit that parameter, as we have been doing, if we omit that argument, as we have been doing, it's launching the kernel into something called the null stream. Again, we're going to talk about what the null stream is in just a moment. But in this case, we're launching the kernel into a named stream, stream 2. And stream 2 is different than stream 1. Therefore, our CUDA syntax, our CUDA semantics number 2 applies. Items issued into separate streams, in other words, these 2 operations, CUDA memcopy async and the kernel call, have no defined ordering relationship to each other. Even though the CUDA memcopy async operation appears first in our source code, it could execute after the kernel. It could execute during the kernel call. It could execute before the kernel call. There is no specified relationship by CUDA. Okay? Now, that might sound a little bit scary. Let's hold on to that emotion for just a moment, because we're going to learn how to manage this beast. Okay? But nevertheless, we need to break that ordering relationship, as we'll see, in order to achieve the concurrency scenarios that we are after. Now, just to complete our review of the syntax, there's a few other things that we might want to do. We can do something called a CUDA stream query. This basically returns, it's not actually a Boolean, it's an enum type, but nevertheless, the result is a Boolean result that says, yes, the stream is idle, or no, the stream is not idle. And that could be useful for some scenarios. It's well beyond the scope of what we want to talk about here. Another thing we can do is something called a CUDA stream synchronize. We know what a CUDA device synchronize is. That says, wait for all CUDA activity issued to this device to complete. In other words, block the CPU thread until all CUDA activity issued to this device is complete. That's CUDA device synchronize. CUDA stream synchronize is straightforward based on that. It says, wait until all CUDA activity issued into this stream is complete before allowing the CPU thread to continue. So it's also typically blocking of the CPU thread, but it's blocking on the activity in a stream rather than device-wide. Lastly, since a stream is a created type, a created entity, we also have a corresponding API to destroy it. That is essentially the free operation. Okay, let's continue. So again, what we want to do on this slide and the next slide is build our understanding of streams by looking at examples. And we're going to be looking at these examples in different ways. So on this slide, what we'd like to do is we're going to pretend that the text in black on the left-hand side of the slide represents our issue order. That's our source code. Okay? And so to take the first example, somehow in our source code, we're issuing a kernel into stream 1, then a memcopy operation into stream 1, then a kernel into stream 2, then a memcopy operation into stream 2. And when I say memcopy, I mean CUDA memcopy async. So all of these operations issued in black on the left-hand side, as if they were issued in that order in our source code, are all asynchronous. None of them block the CPU thread. And then we're going to ask the question, how should these things look? What will the resulting execution timeline look like based on this configuration, this issue order with these streams? So we can imagine already that we've created streams 1 and 2 already, and we have some definition for the kernel and so on. And so if we issue, in our first example, if we issue kernel 1, kernel into stream 1, then memcopy into stream 1, then kernel into stream 2, then memcopy into stream 2, our timeline could look like what we see on the right. The kernel issued into stream 1 presumably will begin executing soon on the device. The kernel issued into stream 2 could execute at the same time, or it might execute after. The memcopy operation issued into stream 1 is going to hinge on our first stream semantics, which says operations issued into the same stream serialized. So by guaranteed, memcopy issued into stream 1 cannot begin until the kernel issued into stream 1 is complete. And likewise, the memcopy issued into stream 2 cannot begin until the kernel issued into stream 2 is complete. But with respect to stream 2 and stream 1, those operations can overlap. Kernel 2 can overlap with M1, and kernel 2, even though we're not depicting it here, could even overlap with K1. Let's go to our next example. Now we've got the same 4 operations, except the stream is slightly different, so we're issuing, I'm sorry, the issue order is slightly different, but it's the same 4 operations. And because of the asynchronous nature of these, none of them are blocking the CPU threads, we're essentially dumping all these operations into one or several queues. And therefore, the potential timeline could look exactly the same. Okay, and later on, I may remember to talk about something called depth first versus breadth first issue order. We'll take a closer look at that, or at least another look at that. But nevertheless, what we're observing here is that issue order may not matter much if I've done a proper job of organizing my stream association. Issue order may or may not matter that much in terms of the actual execution behavior on the device in my timeline. If I execute kernel 1 and then memcopy into stream 1 and then a memcopy into stream 2, let's pretend that these memcopies are in the same direction. We know that the memcopy issued into stream 1 cannot begin until the kernel into stream 1 has completed. And what we'll observe typically is that the memcopy into stream 2, since it's in the same direction, is going to wait for the memcopy in stream 1 to complete. There's not really any guarantee of that according to the CUDA programming model. So it's possible that the M2 and M1 could reverse there, according to CUDA stream semantics. And if those 2 operations are in different directions, we would probably expect them to overlap. So the examples that I'm depicting in orange here are not the only possible realizations. Okay, the asynchronous nature and the characteristics of my CUDA stream semantics number 2, which specifies that there's no relationship between items issued into separate streams, means that there's a number of outcomes that are possible. Okay, You'll have these slides, so I'm going to leave the remaining 2 examples for you guys to think about if you review the slides. And let's continue with our next example, which is going to get down into some nitty-gritty details. Okay, so what we'd like to do now is put everything that we've learned together with some actual source code for what I would describe as a real-world problem. So in the real world, just like we talked about on our very first slide, we very often issue some work to the GPU, and that means we have to copy data first, issue the work, and then copy results back. And if we issue that naively, as we've depicted on the top of this slide, top half of this slide, the code on the right is what I'm calling the non-streamed code. That's basically, presumably, the code you have written if I asked you to do this on one of the previous homework assignments. Okay? You would have written code that looks something like that. And you would have observed a timeline. If you use the profiler, you would have observed a timeline that looks like what you see on the top half of the slide. However, for an operation, let's just pretend that we have an operation that's we're going to refer to as vector math. The idea is we've got a mathematical operation that we're performing on a big, long vector, and it's separable, it's independent. That means that I can do the operations on vector elements 1 through 10 without having vector elements 11 through 20 or any other vector elements. That's a characteristic of an operation that we learned about called independence. Okay? And so when we have an independent operation, let's say it's on vector math, then what we've got is a big, long vector that I need to transfer to the GPU, and then a kernel that's going to operate on all those vector elements, and then we're going to copy the results back. Presumably, maybe the results are in the form of a vector as well. You could even think of a vector add, which is an example that we used a couple times in our previous sessions as an example of this. Okay, so if we wanted to take a vector add and do this kind of overlap, and we understand, hopefully pictorially, looking at this slide, we understand why we want to do this. If we can achieve the overlap behavior that we see on the bottom of the slide, then we've reduced the overall timeline of our code. We've shortened our overall execution time, therefore things are now running faster, and that's what we're all here for. So we're going to use streams to enable this form of overlap, and we're also going to depend on the fact that this operation is independent and separable. So we're going to break our vector math into pieces, chunks, and we're going to transfer a chunk at a time, and after we've transferred that chunk, we're going to launch a smaller kernel, could really be the same kernel, it's just operating on a smaller chunk of data, but we're going to launch that smaller kernel to operate on that chunk of data, and then we're going to copy the results from that chunk back, and then we're going to do this chunking operation over and over and over again. And what we want to do is use streams so that much of our green operation can overlap with much of our orange operation can overlap with much of our blue operation. So the code on the right is designed to do exactly that, where it says streamed. And we're going to walk through that and point out some of the important characteristics. One of the things I want to mention is that this is basically a homework assignment. So one of the 2 examples that you have in the homework is this slide. Okay, so if you can understand what's going on this slide, you should be well on your way to being able to complete that homework problem. Okay, so we have decided we're going to break this problem up into chunks, and so we're going to use a loop to process each chunk. Okay, and we know that each chunk is essentially a microcosm of what we see on the top. We need to do some of the green work, copy to the device. We need to do some of the orange work, process the data, and we need to do some of the blue work for each chunk. Okay, and so therefore our loop is going to proceed from left to right, chunk by chunk. The first thing that we have to do with each chunk is a CUDA memcopy async operation, and so that's the first operation that appears in our loop. We're issuing that into a particular stream. The next thing we have to do with that chunk is run the kernel code on it. And we know that we don't want that kernel to begin until that green chunk transfer has completed. So which of the 2 CUDA stream semantics do we use for that? We use number 1. Items issued in the same stream will execute in issue order. We want our kernel to not begin until the previous CUDA memcopy async operation is completed on that chunk, and therefore we're going to issue that kernel into the same stream. Likewise, when that kernel is finished and we want to copy the results back, we don't want to begin copying those results back until the kernel is complete. We're going to use the same stream semantics to achieve that. Number one, items issued into the same stream execute in issue order. So with respect to our first chunk, we're going to issue all of those into a particular stream. You can see the stream parameter as each pass through the loop is the same. For each loop iteration, it is the same stream for all three of these operations, for the CUDA memcopy host to device, CUDA memcopy device to host, and the kernel. They're all within a particular loop iteration. They're all using the same stream. Therefore, they're all going to serialize. And that serialization along the same stream ID is what I'm depicting in the diagram on the left with the slanted gray lines. So the processing proceeds along the slanted gray lines. And each one of those slanted gray lines represents a particular stream ID. Now, I've called them 0 and 1 here. Let's not get hung up on 0 and 1. Let's just assume that one is called stream 1 and one is called stream 2, or one is called stream 0 and one is called stream 1, and I've created those streams appropriately. In fact, I could use an array of streams as I've depicted in the code on the right. Okay, so with respect to that array index, the stream at index 0 is the one I'm going to use first, and that stream at index 0 is going to guarantee the serialization of the three operations that are intersected by that gray line on the left. Okay, that's my first loop iteration. And then I go back and repeat my for loop for the next iteration, and now I'm processing my next chunk, and I'm using another stream in my array of streams. And I repeat this operation from left to right. And the net effect when I organize my code this way on the right is that I am able to achieve the overlap that's depicted on the left. Now, the sizes of these blocks and exactly the way this pattern looks is going to be dependent on how much data I'm transferring and how long does my kernel take to execute. So people who have a trivial operation like a vector add are going to observe that those orange lines shrink to approximately 0 width. Okay, and so you'll have a bunch of CUDA memcopy and a bunch of tiny little orange lines representing my kernels, and then you'll have your CUDA memcopy device to host. Okay, so I'm not saying that this is exactly the way every operation will look. It depends on exactly what you're doing, how much data you're transferring, and how long your kernel takes to process. But nevertheless, you can get overlapping behavior. Now, the last thing I'll say on this slide is I would call this a depth-first issue order. What do I mean by that? What I mean is I'm going to use the depth direction as being the downward direction. Okay? Depth means moving from top to bottom, green to orange to blue. And you can see that my issue order in my for loop is a green, orange, blue issue order. Green, orange, blue, green, orange, blue, green, orange, blue. I'm going to call that a depth-first issue order. We go through the depth before proceeding fully across the breadth or the width of the operation. It's possible, it should be possible. One of the things we observed on the previous slide is that I can achieve the same concurrency. In some cases, I can achieve the same concurrency scenarios using two different issue orders. And if you think carefully about our stream semantics 1 and 2, you'll see why this ought to be possible. In this case, we could realize this code differently. I'm not going to depict it, but we could realize this code differently with 3 for loops, one of which issues the green bar in its entirety. So it's a for loop of nothing but CUDA memcopy async from host to device, chunked. Okay, we can't do it all in one operation. We have to do it chunked. But we have a for loop that issues all those chunks of green operations horizontally. We would call that a breadth-first issue order. And then we would have another for loop that just issues the kernel calls chunked. And then we would have another for loop that issues the blue CUDA memcopy asyncs in the reverse direction, chunked. If we issued it that way with 3 for loops, I would refer to that as breadth-first issue order. To a first-order approximation, both of those are possible, and both of those should give the possibility of realizing the same diagram on the left, the same concurrency picture. Now, there's details and limitations to this, okay? So that's a particular reason. If I have a very large sequence, of CUDA memcopy async and a very large sequence of kernel calls, I may run out of queue depth. And that would be something that would be problematic. It will still work, but you're not going to achieve the concurrency scenario. So in my opinion, the depth first issue order is to be commended for the fact that it's generally more flexible and is more likely to give you the desired realized concurrency pattern. But we don't have the time to unpack that completely. Okay. Let me pause now, and as you digest that, I'm going to address some of the questions that are in the chat. The next question appears to be, won't you be hit by many more kernel offloading penalties like this? I don't know exactly what kernel offloading penalties is, but I'm going to assume we're going to refer to that as kernel launch latency, in other words, CPU overhead. It's a good question, and this scenario is actually better than the previous scenario, because in the previous scenario, the kernel launch overhead was actually something that would have manifested itself as a minuscule bar in between the hosted device copy and the big orange kernel code. In this scenario, we're not really breaking it up, but we're basically putting that kernel launch overhead where it can be overlapped with other operations, namely host to device and device to host copies. So even though the kernel launch overhead may stagger the orange bar a little bit in my diagram on the bottom half of the slide, nevertheless, this is still hugely better than the previous example where I was just doing everything serially, okay? Even if there is a small cost to additional kernel launch overheads, this streamed approach is hugely better than the non-streamed approach, okay? All right, how expensive is stream creation? Let's just say it's expensive. And so that's a really good question, because any sort of creation, or in my opinion, allocation operation, this is a great question, is something you want to get outside of your performance loop. What is the performance loop? The performance loop is the streamed for loop that I've depicted on the right-hand side. This is the area where you're carefully crafting your code to achieve a particular concurrency and overlap scenario. You don't want anything to disrupt that. So let's take another example before we talk about stream creation. Let's talk about CUDA malloc. Does CUDA malloc take a stream parameter? No, it does not. Therefore, we immediately are posed with the question, well, what is its behavior if I'm issuing it into a carefully crafted concurrency scenario like this? What if I stuck a CUDA malloc in that for loop? I'm not going to delve into that into detail, but basically the wheels will come off. The whole thing will break. It doesn't mean you'll get the wrong answer, but it means that you will not achieve the desired pattern that's depicted on the left. Stream creation is also something that can cause the wheels to come off, okay? So any sort of allocation, stream creations, or one-time overhead type operations, get them out of this for loop. Whatever you have to do, reuse allocations, stand on your head, whatever you have to do, get them out of this for loop. The only thing ideally that you want in this for loop are the things that are clearly understood with stream semantics, that you don't have to go looking at the reference manual to ask the question, what is the behavior of this thing if I launch it here? You want to focus on kernel launches and memory copies and ideally get your concurrency scenario down to just that. Okay. Can a kernel issued in stream 2 access memory issued in stream 1? Yes. And a kernel issued in stream 2, assuming it's on the same device, we'll talk about multi-GPU later, but assuming it's on the same device, a kernel issued in stream 2 can access any CUDA malloc operation that was done on that device, period. Now, does that mean that any sort of concurrency is possible, and therefore I can expect that if I do something in kernel 1, it will automatically be absorbed, the updated value will automatically be absorbed by kernel 2? Not necessarily, okay? CUDA has a weak memory model. We've touched on this briefly previously, and you as a programmer are going to have to make sure that if you're modifying a variable in kernel 1 and you're consuming that modified variable in kernel 2, you probably want to make sure that kernel 2 is issued after kernel 1. In other words, executes after kernel 1. And if kernel 2 is issued into stream 2 and kernel 1 is issued into stream 1, you have not guaranteed that as a CUDA programmer. If kernel 1 is issued into stream 1 and kernel 2 is issued into stream 1, launched after kernel 1, you have guaranteed it as a CUDA programmer, and you should fully expect that modifications that you made to an allocation in kernel 1 will be correctly absorbed by kernel 2. Okay. Is the number of streams limited? Probably it is. I don't happen to know what the limit is, but you don't need 1 million streams. You don't even need 100 streams. You probably don't need 10 streams. Nearly any scenario, if you work at it hard enough, can be handled with literally 2 or 3 streams. If you need 10 streams, you're probably not using streams the best possible way. And if you get to the point where you need 100 streams and you run into a limit, that's your problem. You're realizing your code incorrectly. So yes, there is a limit. I don't happen to know what it is. It's not in the range of 20. If a kernel wants to access a memory chunk which has not yet been copied from the host, what will be the behavior? Undefined. Who knows? I have no idea. You should not ever expect that to give you sensible behavior. And if your code depends on that for correctness, your code's broken. For this example, what size of data and kernel execution time you're considering? Well, I don't really have exact numbers here. The idea is that the H to D copy, the length of the green bar is approximately twice the length of the orange bar, which is approximately the same size as the blue bar. You could imagine a vector add where I'm reading 2 elements, so I have twice as much input data, and therefore the green bar is twice as long as the blue bar. The problem with vector add is the orange kernel will be nowhere near as long as I've depicted here. It will be incredibly short. So for a simple operation like vector add, you can get some benefit from the overlap, but you won't get much benefit from copy and compute overlap. The primary benefit will be from copy from host to device and copy from device to host overlap. Some operations that you might do, a more complex operation like computing a Gaussian PDF function on a vector like we do in the homework, that will cause your kernel to take more time. But there's no specific times except to suggest that the H to D copy is taking twice as long as the kernel, which is approximately the same time. Whether that's all a microsecond, a millisecond, a second, or a year is not relevant to understanding. The optimal number of streams and depth ultimately depend on the code characteristics itself. Yes, but remember, the vast, what's the right way to say this? The underlying CUDA programming model I'm claiming is a 1-2-3 model. You basically have data copying to the device. You've got some sequence of processing going on the device. It might not be 1 kernel. It might be 100 kernels. And then eventually you got some copying back to the host. So those 1, 2, 3 things are what we're imagining are ordered this way. Yes, it will depend on the code characteristic. This one example here doesn't apply to every possible or imaginable use case. I don't know if you need extensive profiling to figure it out, but as we'll see in our next session on analysis-driven optimization, after you've got an initial realization complete, usually a good thing to do is to get out the profiler and study what your code is actually doing. In one of the papers, they estimated stream creation time at 0.03 milliseconds per stream. Great. So that's 30 microseconds, and 30 microseconds could be a long time. If your kernel launch overhead is 5 microseconds, 30 microseconds is a long time. If your kernel execution is a minute, 30 microseconds is nothing. Okay? I still wouldn't write the code that way. I would still go back to what I said, which is get the overhead, the one-time overhead, out of your performance loop. If you want to ignore my advice, you're welcome to do that. If a kernel issued on stream 1 uses all execution units, will the kernels issued on stream 2 be delayed? Yes, and this relates to something that I'm going to call kernel concurrency, and we'll talk about kernel concurrency on a subsequent slide. So I'm not going to drill into it right now, but the answer to your question is yes. Generally speaking, the runtime does not interleave blocks from kernel 2 with kernel 1 if kernel 1 is sufficient to saturate the GPU. I'll come back to that concept. And now I have reached the end of the chat, so I'm going to continue with my my next slide. And I can see right now that we're going to run over, but that's okay. Fortunately, we've got 2 hours, so I'll try and cover this material as quickly as possible. So one thing that we haven't talked too much about is the default stream. I mentioned already that you might not have known it, but you are already using the default stream. There is a default stream, and when you don't use an explicit stream or a created stream, you are using the default stream. When you issue operations into the default stream, whatever they may be, stream semantics apply, and there's some additional characteristics that we're going to talk about, okay? First of all, stream semantics apply, which means that if all you're using is the default stream, like what you would have been doing for any of the assignments up till now, then the only stream semantic that applies is stream semantic number 1, which says items issued into the same stream serialized in issue order, okay? Which is actually good because when you're starting out CUDA programming, the asynchronous nature can be mind-boggling, okay? And so we don't want to just give you a bag of marbles to play with. We want to give you something that's more orderly than that. And so initially when you're starting out, by operating in the default stream, you're effectively having the ordinary C programming semantics that you're familiar with. If I have a line of code in my C program and it's after another line of code, we would expect the second line of code to not begin until the first line of code is done. That is such a basic concept in C programming that even if you took C Programming 101, they probably didn't teach you that, okay? But that's actually a characteristic of the programming model, ignoring things like threading models and OpenMP and all kinds of stuff like that. If we're talking about C Programming 101, it has this stream characteristic, right? That's the way my code executes. And so the default stream behaves that way, just like every other stream. But the default stream, when we're intermixing default stream activity with other created or named stream activity, has some particular characteristics that we want to be aware of. First of all, the default stream will synchronize, which means that it will force all previously issued CUDA activity, no matter what stream it was issued in, to complete before the default stream issued item will begin. That's my first red line in this timeline. Okay. Furthermore, the default stream will require that any other issued activity after the issuance of this default stream item will not begin until the default stream item is complete. Okay. Now, we could go into a lot more details on default streams. I would like to give you some advice. My advice is, as you become a more expert CUDA programmer, use named or created streams and leave the default stream behind. This is unnecessary complexity. I don't know why you would do this when you have the flexibility to use named streams and order everything the way you want. Okay? Now, there might be some situation if you're an expert programmer where you're like, oh, the right thing to do is to use a CUDA memcopy here instead of a CUDA memcopy async. That's exactly what I want, and it's a nice succinct way for me to express what I want. Fine, go ahead and do that. Okay? But in general, if you're trying to organize complex concurrency, don't stick default stream activity in there and try and manage it that way. That's not my advice. Okay, so I would suggest to consider avoiding use of the default stream during complex concurrency scenarios. Create your streams and use only those created streams. And if you see something that doesn't obviously have a stream parameter in your performance critical loop, you should immediately question, why is that there and does it need to be there? Why is that CUDA malloc there? Why is that CUDA stream create there? Do I have to have it there? Is there any other way I can do it? In addition, the default stream behavior is modifiable. In newer versions of CUDA, I think maybe after CUDA 7 or around there, we issued the ability to change the behavior of the default stream to turn it into an ordinary named stream. So it no longer has this synchronizing characteristic, and it will just behave like another named stream. This is just more complexity and more things to worry about. Honestly, I don't see a lot of value there. Okay? The primary value that I know of for this is if you're working with someone else's code and you don't want to rewrite the code, or it's existing in a library, and the code is written to use the default stream, and you would like to sort of jack that up and put it on a named stream, this gives you a straightforward way to do that. Okay? But if you're writing code from scratch, just use named streams. That would be my advice. Okay. Let's continue. There is also the ability, in addition to CUDA memcopy, async, and kernels, we might also ask, is it possible to organize host code so that it has this asynchronous nature and will execute according to stream semantics? The answer is yes. And we use something called a CUDA API call called CUDA launch host func to do that. And what this allows you to do is it allows you to define a host code function that will be issued into a CUDA stream. That means it obeys stream semantics, number 1 and number 2. Semantic number 1, it runs in issue order within that stream. Semantic number 2, there's no defined relationship between the execution of that host code function and any activity issued into another stream. Now, in order for this to work, we can't just have a single CPU thread anymore, okay? Because we're basically saying this host code function could execute at any time. Therefore, I'm going to need another CPU thread to make that possible. And the CUDA runtime launches additional CPU threads to enable this capability. Okay? There's a very important and specific limitation that says within a function that you launch using CUDA launch host func, you're not allowed to use CUDA runtime API calls. I don't want to get into the details there. It's an unfortunate limitation. It is what it is. Okay? So you can't launch kernels there. You can't check status there. You can't do CUDA malloc there. You have to do just host functions. And in addition, if you look at someone else's code, you may see a runtime API call called CUDA stream add callback. CUDA stream add callback, according to the documentation, is in this weird state of being endangered of deprecation in the future. It's not formally deprecated as far as I know, but the documentation states that it has the potential to be deprecated in the future. So now we've got multiple levels of deprecation, but nevertheless, the clue, the hint there is don't use it if you can avoid it. Instead, use CUDA launch host func. Now, just to give you a simplistic example of where this could be useful, very simplistic, I'm not suggesting this is a great example, but we learned that with managed allocations, especially in a demand page virtual memory system, in other words, a post-Pascal regime, to use my previous terminology, where I have demand paging involved in managed memory, we learned that if I launch a CUDA kernel, I can put host code right after that CUDA kernel. And because of the asynchronous nature of the CUDA kernel launch, the host code will begin executing right away. If that host code happens to touch a managed allocation, that's legal, but the kernel may not have begun executing. And so if your host code was depending on the kernel to set some data, and then your host code was going to consume that, really no guarantee that that's going to work. And previously, we had suggested that you might use a CUDA device synchronize after such a kernel launch so that the subsequent host code in this demand-paged managed memory environment would be guaranteed to get the data that was processed by the kernel. Well, another way to do that, CUDA device synchronize is no fun when it comes to arranging concurrency scenarios, okay? We want to avoid that if at all possible. We do not want to stick CUDA device synchronize in our performance-sensitive loop, okay? So what you can do instead is do CUDA launch host func, and this guarantees that my host code that's going to process that data, which is resident in managed memory, will not begin executing until the previously launched kernel is complete, assuming you make the appropriate choices for streams, okay? So that's an example where this type of function could be useful. I'm sure there are plenty of other examples as well, and I believe in my extra reading, I give you a link to an online forum article that discusses a video processing pipeline that uses something like this. Okay, let's see if I can knock down some of these chat questions. Can CUDA streams be used with MPI? Yes, and they probably would and probably should be. And I will talk about that again on some subsequent slides. And or OpenMP threading. Yes, they can be used in both of those scenarios. What is the best way to do that? One stream per rank thread. That's going to get beyond the level of instruction that I'm able to give, but if we have time during the open question session, we can discuss that if you like. Can you say something about thread safety? The CUDA runtime API is thread safe. Let me say that again. The CUDA runtime API is thread safe. What does that mean? That means two different threads, CPU threads, can both issue a call to CUDA malloc, for example, or CUDA malloc in one thread and CUDA memcopy in the other, or whatever you like, and both of those should behave as expected. That's what I mean by thread safe. Can each thread create its own array of streams? Yes. Is there a separate default stream 0 for each thread? Yes. Can we also do it with CUDA stream create with flags, CUDA stream non-blocking? I don't really know what that means. I don't know what it refers to. Let's come back to that question if it's not clear by the end of the session. Let me continue with the slides for now. Okay. So the next topic we want to talk about is what are the implications of this with managed memory? Well, to a first order approximation, I would say follow the same pattern. With managed memory, you know that we don't use CUDA memcopy and we don't use CUDA memcopy async either. What we're going to use is CUDA mem prefetch async. And we learned in our managed memory session that at a very high level from a crude point of view, CUDA mem prefetch async is the analog of CUDA memcopy async in a managed memory scenario. It dictates a transfer or a migration of data, okay? So you're going to follow the same pattern. You're going to use CUDA mem prefetch async, and you should be able to overlap data that's being migrated by CUDA mem prefetch async with kernel calls. And you should be able to overlap migrations in one direction with migrations in the other direction. Again, stream semantics apply. So use stream semantics the way you should in order to guarantee that things execute in the proper order. However, at a detailed level, CUDA mem prefetch async actually has more work to do than CUDA memcopy async. One of the things that we liked or talked about with CUDA memcopy async is that it's handled by an engine. It's actually handled by a hardware engine under the hood, and that means that the hardware engine, when it decides that it's ready to go, has relatively low overhead. The host memory mapping is all fixed, and it can just start grabbing data out of the host and putting it in the device, or it can start grabbing data from device and putting it into host memory. A migration is more involved than that. Migration is movement of data from one place to another. It's based on pages, and it's causing pages in one place to go out of scope and pages in the other place to go in scope. This means that paging tables, both in the source and destination, have to be updated in addition to the movement of data. There's a lot of complexity here. I'm not intending to cover all the complexity with just a few sentences. But nevertheless, it has more work to do, and therefore a migration call can take more time than an ordinary async memcopy operation. This can introduce unexpected gaps in the timeline. Somewhat non-intuitively, this behavior, the impact of this overhead may vary depending on how busy the stream is. Also, somewhat non-intuitively, a busier stream may have lower overhead, let's call it fix-up or page table fix-up overhead for a migration than a non-busy stream. Okay, and there are specific reasons for this which I won't cover at this time, but there's a blog that goes into this in quite a bit of detail. And I suggest if you want to drill into the next level of detail for copy compute overlap with managed memory that you read that blog. Another aside is CUDA event. A CUDA event is an entity, it's an item that can be placed as a marker in a stream. It doesn't cause anything to happen per se, it doesn't modify data, it doesn't cause anything to begin executing or anything like that. It's simply a marker in the stream. As we'll see in a moment, we use something called CUDA event record API to record it, so we will say that the CUDA event has been recorded when it's issued, in other words, when you've issued that call. We'll see what that is in a moment. And I'm going to say that a CUDA event is completed when the stream execution reaches the point at which that marker has been inserted in the stream. So again, you should imagine a stream as something like a timeline or a queue. You're putting items into the stream. They're not necessarily all executing right away. They're going to execute in stream order. But I can stack a whole bunch of things in that stream conceivably before any of them have begun to execute. One of the things that I can stack in that stream with kernels and with memory copy operations is something called an event, which is like a marker, a flag. The most common use that I know of for CUDA event is timing. And so what would that look like? First of all, an event like a stream is a named entity. It's a named type. And so we're first going to declare our names for two CUDA events. They could be anything, but we'll call them start and stop. Then we have to create those, which is registering those names with the CUDA operating system, the CUDA runtime, so that the CUDA runtime knows that they represent these flags that I described, things called events. And then we can record the event. We record the event by name, and in this case, we're issuing it into the default stream, okay, because I've omitted the stream parameter. There is a stream parameter, but I've omitted it. It takes a default quantity of 0. So in this case, I'm issuing it into the default stream, but I could issue it into a different name stream if I had those. And then I launch my kernel, and then I launch another marker or event into the same stream called stop. Once I have those two markers in place, I can do things like I can synchronize on one of those markers. That says, force the CPU thread to stop and wait here until the stop event has completed. Okay, what that means is stream processing has reached the point at which the stop event was recorded. That means in this case that the kernel execution that we've depicted here is complete. So CUDA event synchronize on the stop event means we're waiting, effectively waiting until that kernel is complete. And once that's done, we can do some interesting things, like we can ask the CUDA runtime to say, what was the elapsed time between the completion of the start event and the completion of the stop event? Give me that elapsed time in milliseconds in my variable called floatvar. Okay. Another thing that we can do with events is arrange for complex concurrency scenarios. And we have another API call, which I'll talk about in a subsequent slide, called CUDA stream wait event, which does about what it sounds like. Okay, it says for my stream, which I am naming here, which I am identifying here, cause this stream to wait on this event, which was issued somewhere, either, presumably in another stream. Okay. Event-based timing, as a side note, event-based timing, although I'm depicting it here, can give unexpected results when I'm trying to time host activity or if I am trying to time complex concurrency scenarios. So my advice for timing, even though I've depicted using events for timing here, it's probably the most common way that events are used. My advice is to use, I would say, host-based timing methods to a first-order approximation. Okay, let's continue. Multi-GPU now. We haven't really talked about multi-GPU, but you probably know that systems like Cori and Summit have multiple GPUs in a single node. And so you might have asked, well, could I use them, and how do I use them together? We're going to take a look at that more or less strictly from the standpoint of the CUDA runtime API. My objective here is to teach you CUDA, not to teach you everything, because I would never be done. So you should be aware as we proceed through these next 3 slides that this is starting to scratch the surface of how I might effectively use multi-GPUs to work on in a single code or on a single problem, okay? So I'm going to talk about the aspects of the CUDA runtime API that allow you to access and manipulate multiple GPUs, let's say, at the same time or in the same code. But this is not going to be a complete treatment of answering the question, how should I write a code that effectively uses more than one GPU? Because to answer that question, we'd want to look at topics like, what is the intersection of CUDA and OpenMP? Or what is the intersection of CUDA and MPI? Or some other parallelization strategy that you may be aware of, okay? And we will not be answering those questions in the presentation today. But we're going to expose you to the CUDA runtime API that allows a CPU thread to access multiple devices and use them in an intelligent fashion. Okay, so some of the most basic API calls are depicted first here. CUDA get device count. How many GPUs do I have? Like if I ran this on Summit, I'm pretty sure the answer would come back 6. Okay, now that can be modified depending on some environment variables that get set when your job is launched. So if you run a job on Summit and your job specifies only 1 GPU and you do CUDA get device count, it might return 1. So it's going to be a function of how exactly your code is launched, the environment variables, and the job scheduler that you're using. But it's certainly possible to launch a job on a Summit node and get an answer back of 6 here. Then if I have multiple GPUs, I might ask, well, how do I access them? Well, as it turns out, if I don't use any of this API machinery that I'm talking about right now, I am always and by default using a GPU that is enumerated 0. It's logically the first GPU that's available to me, okay? And most of our work so far has had that in mind. So if I don't use any of this, my code basically has access to one GPU. Everything will run on the first GPU, whichever one that is. But if I wanted to use other GPUs, I would use CUDA set device with a number like 0, 1, 2, 3, 4, or 5 if I was on Summit and I had access to 6 GPUs. I would use CUDA set device 0 to talk to the first device, CUDA set device 1 to talk to the second device, and so on. There might also be a scenario where I'm at a point in the code, or maybe I'm in a function, and I don't know what's gone on in the calling environment. So inside the function, I would say, which device am I currently talking to? If I were to issue a kernel, which device would it go to right now? I can use CUDA get device, and the variable that I pass, or the pointer to the variable I pass, will cause that variable to be populated with the device that is currently set or was most recently set by this thread. Another somewhat related API call is CUDA get device properties. We're not going to go through that in detail, but if you would like to understand what that does, it tells you a lot of things about the GPU that you're currently accessing, or really the GPU that you've specified using the device parameter. If you'd like to learn more about that, I suggest that you study the CUDA sample code called device query. Okay, so if you look up the CUDA sample code called device query, if you just Google that, you'll find it, and it uses this API call and it unpacks it to the nth degree. Okay, it shows you all the different things that you can query at runtime about a GPU. A few other points to be aware of: multiple host threads can share a device, so they can both say CUDA set device 0 and both use CUDA device 0. A single host thread can manage multiple devices, and that would probably be the objective or the focus of this API that we're dealing with. In other words, I can, without using OpenMP or MPI or some other parallelization, host parallelization strategy, I can run work on multiple GPUs from a single host thread. And that's, for the purposes of this topic and what we're dealing with right now in the homework, that's what you'll be doing. So a single host thread can manage multiple devices. You use CUDA set device to select the device. And another thing that we'll talk about in a subsequent slide is CUDA memcopy peer async. Once we have the idea that there may be multiple GPUs that I have, I might then ask the question, well, is there an intelligent way to copy data directly from GPU memory on GPU 0 to GPU memory on GPU 1? Yes, there are ways to do that. We can use CUDA memcopy or CUDA memcopy async to accomplish that. Sorry, that's not true. We have to use CUDA memcopy peer or CUDA memcopy peer async to copy from one device to another device. Okay, so let's keep going. Okay, what about streams with multiple GPUs? It turns out streams and also CUDA event have an implicit or automatic device association. That means when you create a stream, the device that you have most recently set using CUDA set device in that thread will be the stream for which will be the device for which that stream is associated. That stream is usable on that device, it refers to that device, and it has no logical connection to any other device. Therefore, there's an association, and you need to be aware of that. So if you say CUDA set device 0, CUDA stream create stream 1, and then you do CUDA set device 1, and then you try to do something with the stream that you just created, you're going to get errors. If you try to launch a kernel, it won't work. If you try and do CUDA memcopy async with that stream, unless one of the devices, if it's peer async, that won't work either. Okay? So kernel launches will fail if issued into a stream not associated with the current device. Okay. We talked about CUDA stream wait event already. The idea here is that I may issue an event into a particular stream, and I may want to interlock or cause a dependency relationship between CUDA activity in another stream with the activity that's taken place in this stream prior to the issuance of the event. And CUDA stream wait event will allow me to make those interlocks, stream-to-stream interlocks. So this is, in a sense, you could say it's breaking our stream semantic number 2. We stated that items issued into 2 different streams have no defined relationship. However, you as a programmer can build an interlock or a relationship using this API call if you wish to. Because of that, you might want to try and use this call sparingly. Okay, things can get complicated pretty quickly. Another API call you have available to you is CUDA event query, which allows you to tell if that event has been completed or not. So simple device concurrency looks like this. I want to run code on 2 GPUs, quote unquote, at the same time. It might look like this. Okay, CUDA set device 0, create my stream. That stream 0 is now associated with device 0. Then CUDA set device 1, create another stream. That stream 1 is associated with device 1. Then launch my kernel into stream 1 on device 1 because that's the device that I had previously set. And then switch back to device 0 and launch my kernel into stream 0 on device 0. And now I should be able to witness concurrency, in other words, the potential for concurrency, overlap of execution between those 2 kernel launches. There's a number of other things. We're going to talk about kernel concurrency in a moment. So there may be other things that are required, but for 2 separate devices, as we're depicting here, you should be able to witness concurrency that way. And in fact, the homework will expose you to an even simpler method, basically using default streams. We talked about CUDA, memcopy, pure async. The idea is, wouldn't it be nice if I could copy data directly from one GPU to another? The idea here is without going through host memory. Of course, I can copy from one GPU to another if I do a CUDA memcopy from device to host, a host buffer, and then CUDA memcopy host to device to another device. Of course, you can do that, right? That's obvious. But wouldn't it be nice to do a direct transfer, and wouldn't it be nice to do a direct transfer that doesn't depend on any CPU memory at all? The best way to do that is to use CUDA memcopy pure async, and this requires a system topology that supports it. Basically, it means that the 2 GPUs in question can be put into a peer relationship with each other. I'm not going to go through all the system topology details, but it basically means that those 2 GPUs must be on the same fabric, whether that's PCI Express or NVLink. And if you're on Summit, for example, there are basically 2 separate fabrics. There's one NVLink fabric associated with one CPU socket and one NVLink fabric associated with another CPU socket. However, rather than worrying about all that stuff, at runtime, you can simply test whether or not 2 GPUs can be placed into a peer relationship using can access peer. So we're now going to unpack the code. First, we're going to set our device to device 0, and we're going to say CUDA device can access peer to a variable, which is going to give me a yes/no answer as to whether or not devices 0 and 1 can be placed in a peer relationship. And if they can, then I'm going to enable peer access in both directions. That's what the next 2 enable peer access calls do with the CUDA set device in between. So CUDA enable peer access, the first one, because I set device 0, is enabling access from 0 to 1, and the next one is from 1 to 0. Okay, that's needed so that it transfers in both directions. If you know that you're only going to transfer in one direction, you don't need both of those. Okay. So once I have those 2 peer access paths enabled, then I can do my CUDA memcopy peer async, and that data will flow directly from one GPU to the other. There are limits on the number of devices that can be placed in a peer click. A peer click with respect to a device, a peer click is how many other devices do I have enabled peer access to. Okay, that is my click for that device. And that number is limited to something like 8 or 9. I think it's 9. Okay, I think we've covered everything on here, and if this all works, then it means there are no transfers of data into or out of host buffers. All of the data flows directly from GPU memory on device 0 across the fabric directly to GPU memory on device 1, and that's the fastest way to go. And that completes our multi-GPU discussion. Remember, we didn't talk about, in that very brief discussion, we haven't talked about other things which are typically important, relevant, or used when we're dealing with a multi-GPU processing scenario. Very often, we will want to use OpenMP or MPI. And those to a first order description are roughly orthogonal. By orthogonal, I mean they can be used together. Okay? The runtime API doesn't interfere with OpenMP, and OpenMP doesn't interfere with the runtime API. Now, the details of that are obviously a lot more complicated than that, but to a first order approximation, you should assume that both MPI and OpenMP can be used quite flexibly with CUDA. Okay? But this is not a full treatment of that topic. Okay, there's just a couple other relatively minor concurrency scenarios to talk about. One of them is one that we've run into already without perhaps calling it that or realizing it, and that is that a kernel launch, pretty much any way I do it, is asynchronous, and therefore the CPU code that runs right after the kernel launch is going to run right away. In other words, concurrently with that kernel execution. And so this is what we would call a basic kind of host device concurrency. Okay? I can't reverse those and see the same thing. If I put the CPU function before the kernel call, then the CPU function will execute completely before the host code gets to the kernel call to launch the kernel. Those won't execute concurrently. But this way, where the CPU function is under the wing of the kernel, so to speak, that CPU function has the ability to execute concurrently with the kernel execution. The other one, which I kind of hesitate to talk about because people really get hung up on this, and that is concurrent kernels. If I issue two kernels, let's say on the same device, if I issue two kernels into separate streams, those kernels have the potential to execute at the same time. Now, a lot of people latch onto this idea and go, oh, I can get more performance that way. And in fact, if I can run two kernels concurrently, why not run 4 or 8 or 16 or a million? Obviously, this defies logic. Okay? The GPU does not have infinite capacity. And if there's any logic to the idea that I can run two kernels and expect them both to run just because I managed to get one kernel to run, then exactly the same logic applies to 32 kernels instead of 16. Okay, so there's a logical breakdown in this thought process to begin with that I want you to be aware of. And that logical breakdown is predicated on the idea that the GPU does not have infinite capacity. Even if I satisfy every necessary condition for concurrency, it's not guaranteed that I'm going to witness concurrency. And in particular, that's true for concurrent kernels. Now, the most obvious reason why concurrent kernels may not execute concurrently is if I have exhausted a GPU resource for kernel execution. So, for example, a GPU has a limited number of SMs. If all of those SMs are full, there's no reason to assume that other blocks can begin executing, even if I've satisfied the requirements for concurrency. And generally speaking, although it's not specified, the kernel launch engine or the work distributor, the CWD, the CUDA work distributor, which is an engine inside the GPU, will generally distribute blocks from kernel A before distributing blocks from kernel B if kernel B was issued after A, even if A and B are otherwise satisfying the requirements for concurrency, meaning they're in separate streams. Okay? Generally speaking, the CUDA work distributor will launch or schedule blocks onto SMs from kernel A before kernel B in issue order. That's not specified. It's not required to be that way, but it's typically what we observe. So if kernel A has a whole bunch of blocks, there's no reason to assume, first of all, that all of kernel A will get scheduled. Nevertheless, kernel B. Okay? So if I have a number of blocks that's 1,000 in my first kernel launch here, and my number of blocks in my second kernel is 5, there's no reason to assume that blocks from kernel 5 are going to intermingle and butt their way to the head of the line before blocks from kernel A, the first kernel. It just doesn't work that way. It's not because it's not specified. In fact, there's no specification. Those blocks can issue in any order and be legal according to the CUDA programming model. But what we observe is the CUDA work distributor will attempt to exhaust the blocks from the first kernel before going to the blocks of the second kernel. And therefore, if there's lots of blocks or lots of threads or lots of some other thing in that kernel that consumes a critical execution resource like shared memory or registers, then my first kernel can fully saturate the GPU, leaving no room for the second kernel. It's not to say that you did something wrong, but you're not witnessing concurrency because there's no opportunity for it. Okay? And in many cases when people ask questions about this, that's what they're tripping over. Okay? So in order to witness concurrency, you basically need relatively small kernels in terms of their resource consumption that execute for a relatively long time. Then you can actually witness in the profiler concurrency. Now, if those two kernels are issued to two separate devices, you can forget all that, right? And your homework will provide an example of that. Okay. We're almost done. Stream priority. So now that we know what streams are, we have an optional ability to specify a priority. And what the priority does is it informs the CUDA work distributor to say, okay, I've launched a kernel from stream A, and I've launched another kernel into stream B. Therefore, those two kernels could execute concurrently. But what I would like you to do is preferentially select blocks from kernel B to deposit into SMs before you select blocks from kernel A. The way to accomplish that in a program-aware way is to use something called stream priority. You will assign a priority to a particular stream, and if that priority is above the assigned priority for another stream, if both of those blocks are available to the CUDA work distributor, the CUDA work distributor will preferentially, when the opportunity to schedule a new block on an SM occurs, the CUDA work distributor will preferentially select a block from the higher priority stream. There's no statement about preemption. There's no statement that says a higher priority stream preempts a lower priority stream. Okay? And if I have enough elapsed time between the issuance of the low priority kernel and the high priority kernel, the CUDA work distributor may finish the execution of the low priority kernel before you even informed that there was this high priority kernel. Okay? So you're going to have to meet some requirements in order to actually observe stream priorities in effect. Okay? But nevertheless, the possibility exists, and the method to do it is here. First of all, you're going to have to create the stream with priority, and you can get the priority range that's available. Currently, according to my knowledge right now, this could change in the future. There's actually only two priorities, basically a low and a high priority. So you basically only have one level of priority, but you can have a high priority stream that can basically take precedence in terms of block issue order, can take precedence over a low priority stream. Okay, and the syntax is here on this slide. Let's not go through it in detail. Last topic before we wrap up is CUDA graphs. And graphs is a new feature in CUDA 10. What it allows you to do is specify a sequence or a collection of activity. And this activity can consist of kernels, memory copy operations, callbacks, by that I'm referring to host code, and even other graphs that are executed according to a particular graph specified relationship. So each work item, that would be a kernel or a memcopy operation or something like that, is a node in the graph. And you can specify a kernel as a node or a memcopy operation as a node and so on. And it also allows you to specify dependencies. So the idea behind dependency is basically in a graph way, you're saying these three nodes in the graph must finish their activity before this other node is allowed to begin. And so the way that you think of that dependency graphically is via an edge in the graph. So a node is like a point in the graph, a dependency is the edge in the graph, and the edge specifies the dependency relationship. Okay. Once it's defined, so the definition of the graph is sort of done in a sense offline. By that I mean you do it without actually executing anything, without actually performing any work. Typically you define a graph that way. And once it's defined, you can reuse that definition over and over again. So this allows you to conglomerate a collection of work and treat it as a single entity, a graph. That in and of itself might be interesting. It's sort of a level of abstraction. The other benefit that people typically are interested in when they're motivated to use graphs is a reduction in the time it takes to issue work. So the time it takes to issue work is what we like if we're talking about a kernel, we would refer to that as a CUDA kernel launch overhead or launch latency. other operations have latencies. And the graph mechanism allows some of those latencies to be compressed or eliminated. Now, getting into all the details there is well beyond the scope of what we're trying to cover here. But what I want to do is alert you to the fact that this graph API exists. There's graph CUDA sample codes. There's a graph section in the programming guide. And if something like that sounds interesting to you, you may want to explore it. Okay. So with that, I think we are at the end of our material. We only have 2 sessions left. Our next session in August will be on analysis-driven optimization, and the one after that will be on cooperative groups. One comment I'll make about analysis-driven optimization is, if you've been doing the homework, you've had some exposure to the profiler tool called Nsight Compute. And in this homework session, we'll introduce you to Nsight Systems, which is the other profiler tool. And those profiler tools have sort of a relationship or an ordering with respect to each other. We'll explore that in the next session, but if you do the homework here, you'll have a nice preview of what is Nsight Systems, which will be a good lead-in to the next session, since you hopefully already have some exposure to Nsight Compute. So with that, we have further study and the homework. So I'm going to now pause and try and click through our questions that I have left in the chat, and we'll take any spoken questions if there are any. And if there is any time left, I apologize, Max. If there's any time left, I will turn it over to Max for the homework. Let's see. Use CUDA stream create with flags to create streams such that activities on them will not be blocked by activities on the default stream. Yes, you can do that. Yes, you can do that. The answer is yes. How is the CUDA event API same, different from NVTX markers? Okay. An NVTX marker is something that's primarily associated with profiling activity, and there is definitely similarity to a CUDA event. An NVTX marker is a marker, or a flag, just like a CUDA event is. But the NVTX marker is primarily visible to the profiler, but not primarily visible to the runtime API. Okay, so that's one difference. And also, the things that you can do with NVTX markers are somewhat different than the things that you can do with a CUDA event. Like, I couldn't use a TX marker within my code to measure elapsed time. I can do it in the profiler, but not within my code. Within the profiler, I can use an NVTX marker to do things like measure elapsed time, and I can also do things like creating ranges. Okay, that's not exactly the same thing as a marker, but it's a related idea, and those are the types of things that you might do in a profiler so that you can have a shaded range in your code or a delineated section in your code so that you know when something started executing and when it finished executing. Okay, is it possible to use CUDA events to sync? Yes, it is, between different streams, and I talked about that in the presentation. The way that you would do that is on using a runtime API call called CUDA stream wait event. So if that's not clear, I suggest that you review the presentation again. But CUDA stream wait event does pretty much what it sounds like. I launch an event into a stream, let's call that stream A. And later on in stream B, I say CUDA stream wait event, and I mention my event that I launched into stream A. That means CUDA stream wait event, the stream B, at that point, the execution will be held up, the stream execution, the GPU activity, will be held up until the event launched into stream A is marked as completed. In other words, as the CUDA processing activity in stream A reaches the point at which that event was recorded. At that point, the CUDA stream wait event function will no longer block stream activity, and stream activity in stream B can continue. So the answer is yes. Can you comment on using CUDA math libraries with multiple GPUs? The basic CUDA math libraries, the things that provide you with the function like the ability to do a square root or something like that, are pertinent to a single CUDA thread and therefore have no knowledge of multi-GPU activity. I assume that the CUDA math libraries you're referring to are things like cuBLAS and cuFFT. Both of those libraries, linear algebra library and FFT library, have the ability to do work on multiple GPUs. That means I can do a large FFT that's spread across multiple GPUs and perhaps get a couple benefits. The first benefit is I might have more memory, GPU memory, to store the FFT data. And secondly, hopefully the FFT data will be produced more quickly. So that's the basic idea behind there. That's the cuffed XT API. It's documented in the cuffed manual, the cuFFT manual. cuBLAS has a somewhat similar subsystem that allows you to do multi-GPU activity. Like, for instance, I could do a matrix multiply on multiple GPUs. And one of the benefits there, one of the interesting characteristics of the cuBLAS multi-GPU API is that I can actually work on a matrix size for that example. I can actually work on a matrix size that's bigger than all of my collective GPU memory. As long as it can fit in CPU memory, the cuBLAS multi-GPU API can actually parcel or chunk up that matrix and perform the matrix multiply operation using multiple GPUs on chunks and assemble your complete result that way. So that's an interesting characteristic there. But yes, both FFT and cuBLAS have the ability within the library to use multiple GPUs. Can a kernel wait for event synchronization within device code? No, it cannot. Or can this only be done on the host? It's only with respect to, it's not intra-kernel, it's at the extra-kernel level, it's at the stream level. In other words, it's relevant not just to host code, but things that are executing on the device. Those things that are executing on the device, like a kernel as an entirety, or a memcopy operation as an entirety, can wait on an event, and I described one way that that could happen. But within device code, I cannot query an event or anything like that. Now, this gets complicated because the device code has the ability to create streams. The device code, CUDA device code, has something called a device runtime API, which is documented in the programming manual, which we have not talked about. It's closely related to something called CUDA dynamic parallelism, which we have not talked about, but which in a nutshell is the ability to launch a kernel from device code. And the CUDA device runtime provides for a certain subset of capabilities, like, for instance, creation of streams. And if you get into understanding how to use CUDA dynamic parallelism, you might understand why it might be interesting to have streams at that level. But this topic is well beyond what I intend to cover today. And even if there is any similarity, which there is, streams created on the device and streams created on the host are two completely separate animals. One does not know of the other. One cannot query the other. And that applies for events and anything else. I think I've answered that. The last question is, are you aware of NVIDIA CUDA math libraries using concurrent kernels? I am not. I'm not saying it doesn't exist or can't happen. I'm just not aware of it. And hopefully, you might have an idea of why that might be already. In other words, concurrent kernels are not fundamentally a way to achieve higher performance on the GPU. The way to achieve the highest possible performance on the GPU is to saturate the GPU with a single kernel. You cannot beat that with multiple kernels executing at the same time. Can't be done. That's my advice. Feel free to try and disprove me. Now, that statement was predicated on the idea that I have a type of work which can be issued in such a way to saturate the GPU from a single kernel. If I have that as a starting point, that's absolutely the best way to go. The reason concurrent kernels enter the fray is because in some situations, my work creation or work issuance doesn't allow or permit that. In other words, I may be creating work in relatively small chunks that I would like to begin executing on the GPU, but those small chunks of work are not sufficient to saturate the GPU. And in that case, as compared to running those small chunks of work sequentially, concurrent kernels can certainly give you an improvement in performance, certainly. Okay? That's the primary place where concurrent kernels should be considered, in my opinion. is when there is some nature of my work organization that prevents me from aggregating work to the point that I can saturate the GPU, and instead I have a strongly preferred work issuance strategy that says I want to issue work in small chunks. If that is the case, then concurrent kernels is something to be desired wherever possible, okay? But the CUDA math libraries, you know, they're not primarily designed to execute a 32-point FFT. You're just not going to get interesting performance that way, okay? So if you're executing a 1 million point FFT, which is where cuFFT is going to start to become interesting, you have enough work to saturate any GPU, okay? That's all the way through A100. You have enough work to saturate any GPU with a 1 million point FFT. Now, what if you have a batched FFT? What if you have 1,000 batches of 1,000 point FFTs? I don't know exactly how CUF does that under the hood. It might be that they use concurrent kernels. I kind of doubt it, but maybe they do. And if you want to use a profiler, you can explore the behavior of CUF, or any library for that matter, in various scenarios. Okay, so with that, I'm at the end of my talk. Unfortunately, there's not much time left. Max, if you're on, could you quickly let me know if you think it's even worthwhile to talk about the homework, or should I just use the remaining 9 minutes to talk about questions?
Yeah, I can go through the homework for just a few minutes.
Great. I'm going to turn it over to Max then. Thank you, Max.
All right, if you could stop your screen share.
Yeah, I will stop sharing.
Okay, so for today, we're going to be working with the homework session that is available on the standard OLCF webpage. So if you were to, I have it up here, if you take a look, you can see that this is the main webpage for the course. And if you go down to the exercises, it brings you to the link for the repo. So if you've done the previous homeworks, this should be familiar to you. You'll see that we have exercises, and then the one for today is in homework 7. As with any Git repository, you can clone this. And so what I have done is I have cloned this repository on Cori. So I have a allocation on Cori that I have done using this command here, or something similar to this command here. I'm sorry, I used the salloc command to get myself an interactive node on Cori. If you're a Summit user, you'd of course continue to use the bsub command that you've used in previous homeworks. Now, I just want to take a couple minutes to demonstrate how to use the NSYS Systems profiler so that when you go through and do the homework, you have a sense of what to look for. So I'm just going to run through the first step of the first homework assignment so you can know what to look for, and then you'll go ahead on your own after the session and then try out the coding experiment for yourself. So if you were to clone the assignment, you would see that you have in your directory, in the homework 7 directory, you have 2 files, overlap.cu and multi.cu. So overlap.cu is the one that we're going to start with. If you open up overlap.cu and look at the code, you can study this on your own. It has a kernel that does some work. Bob mentioned in his talk that it's computing something like the average value of Gaussian PDF. I won't go through what that does. But what I'm going to look at is the main function, just to give you a sense of what's going on here. So in main, we allocate some memory on the host and the device. We create some streams. And so this is creating an array of streams like you saw in the lecture. We have a warm-up kernel, and then we have an actual kernel that we do that does the compute for computing the average of this Gaussian PDF over some range of input points. Now, this code here already works, and if you compile it, it will compile and run. And the homework assignment is in 2 phases. First, you're going to run this code and collect the profile. And then the second part of the homework is to take this code here inside this ifdef, which is currently non-working, because you can see that you have some fixed-B statements here, to do a similar operation, but using multiple streams so that you can overlap, copy, and compute. And so you can see this kind of standard scenario here where you have a memcopy async from the host to the device, and then a kernel on that chunk of the data, and then you copy that chunk back from the device to the host. And so in principle, this ought to demonstrate an overlap between copy and compute. But before that, if you don't have that part done, because that's the second part, is to do that code, if you don't have that done, you can at least compile the code as is, doing the standard MVCC command to get the overlap binary. And at least on Cori, I can run it like so and verify that I get a correct answer, hopefully, and that no CUDA errors are reported. So you can see no CUDA errors were reported. I had a time emitted for how long it took to run that series of memcopy and then kernels. Now, what we're going to do is use the Nsight Systems profiler to collect a profile of this application. So there's two ways that you can use Nsight Systems. You can either use it at the command line or you can use the user interface, and we're going to recommend that you use both. And one way that you can do both at the same time is to use the following command. So nsys profile, nsys is the name of the command line tool that collects the profile. Nsys profile means that I want to collect the profile of the application and save it in a file, and the file name will be automatically generated. In this case, because I didn't specify it, it'll be something like report1.qdrep. We'll see that in a moment. And then --stats equals true means that I want to post-process that report at the end to get a summary to standard out of what's going on in the application. And so you can see that we get a summary of all the CUDA APIs that were called. So you can see your calls to CUDA stream create. You can see the calls to CUDA host alloc and CUDA launch kernel, which is the underlying API call that's generated by the triple chevron syntax. You can see that there were two calls to the kernel, Gaussian PDF. This nicely matches our expectation that we had a warm-up call and the actual call that we timed. And then you can also see a listing of the host to device and device to host copies. But what I really want to show you is what this looks like in the user interface. And so note here that it says that it saved a report file, and it gives me the full path of that report file. So what I'm going to choose to do is copy this down from the remote system to my desktop system. And so I can just use SCP to do that. I can give it the remote path to the file and then copy it down to my little system. So you now see I have report1.qdrep on my system. I happen to already have Nsight Systems installed and downloaded. If you don't, you can get it from the NVIDIA Developer Zone. It's a free download. You just need to register. Or you can get this if you have the CUDA toolkit installed. It also comes as part of the CUDA toolkit. So I would go to File and then Open. And I happen to already have the right directory for this profile. Otherwise, you just navigate to that directory on your system. And then you would open up this report by just double clicking it or by clicking it and selecting File and Open. And then you get a view like this. So in this view, on the top half of the screen, you have information about what happened from the CPU's perspective. So you can see calls into the OS runtime. You can see the load on the CPU threads. This is similar to what you might get up here, for example, if you were to have top open while the program was running. And then on the bottom part of the profile, we have information about what happened on the GPU. So this is like the GPU's perspective. It will show you mem copies and kernels as they occur from the GPU. And so, for example, if you had a CUDA mem copy, then I would expect to see the CUDA mem copy appear in the CUDA API row. And then at the same time down here in the CUDA row, I would expect to see the actual mem copy operation. If you had a CUDA mem copy async, for example, you would see a similar thing, although it could be offset to the right because the nature of asynchronous operations is that they don't have to occur at the same time as they're launched from the host on the device. Now, this profile, you can see from left to right, we have a timeline. And so this application ran for about 2 seconds of wall time. And all of the GPU activity occurred in this chunk here and then in this small chunk here. For the rest of the time, this row is blank. And so these are other operations. You can look up here and see, for example, this first chunk of the timeline was calls to CUDA host alloc. And then this chunk of timeline here, we don't know what it is just by looking at the profile. But if you inspect the code, you'll be able to discern that this is when we do some host processing to generate the host data to fill it with random numbers. Now I can zoom in on this part of the profile like so. I'm using holding control down and using my middle mouse wheel. Or if you had a touchpad, you could pinch inward to do this. And if I zoom in, I can then see that I have a CUDA mem copy, and then I have a kernel operation, and then I have a final CUDA mem copy operation. And so what we see here is that this is the initial code that had just a copy and then a kernel and then a copy. And what we'd like to see if we were to expand these rows out is that we have multiple rows of memory and multiple rows of kernels corresponding to each of the independent streams, with the idea that if we were to look at this CUDA row, we could see kernels and mem copies happening at the same time. whereas now the green and pink, which represent mem copies, are happening disjointly with respect to the kernels. So you'll know you have succeeded if you see, for example, some blue happening at the same time as some green or something. So that's what you're going to look for if you make changes to the first homework. I encourage you to go off and try it. And as usual, we have solutions to those assignments there if you want to just try it out that way. All right, thanks everyone, and I hope you enjoyed today's session.
All right, well done covering that in less than 10 minutes, Max, thanks. So does anybody have any questions about what was just covered? Right, if you do, go ahead and drop them in the chat. Otherwise, I would like to thank Max, Robbie, and Bob. Thanks for the homeworks and for a great talk as always, Bob. And we do have a survey on that same page that I dropped a link into on the chat. So if you could fill that out for us, it should take 1 minute to do, and it'll help us to improve events in the future. But otherwise, we will see you at the next event, hopefully, which will be taking place in August. So thank you again, everyone, for joining us and for giving the presentations.